thank you for the host, and thank you to give me this chance to share some of our thinkings about this electromagnetic counterpart for double neutron star mergers. Okay, my name is He Gao. I'm from Beijing Normal University, and Sarah said I have 30 to 40 minutes to give a very brief interview, a very brief introduction, sorry, a very brief introduction to this series about this EM counterpart. Okay, so I guess we all know this story very well. So in almost 4 years ago, we detect the LVC detect the very first binary neutron star merger event, and also the EM community have detected the short gamma burst and optical transient and some X-ray signal and radio signal. So I guess we all know this story, and we all know that I guess if you want ask everybody what's the next multi-messenger candidates, I guess everybody will say maybe it's still double neutron star mergers. Why is that? Because first, we already detect the double neutron star mergers, and the double neutron star systems exist in our galaxy. So we believe that it should be everywhere in the whole universe. And also, when the binary neutron star mergers, we have a lot of materials, and these materials could release energy in different channels. It could give us the GW signal. Also, it could give us a very rich EM signals. So the question is, what's the EM signal looks like from this binary neutron star mergers? That's what we want to talk about. So from a theoretical point of view, we think the signal depends on the product of these mergers. And we always say there are two kinds of product. One is the central product. Okay, so the two neutron star mergers, it depends on the total mass of these two neutron stars, and also depends on the neutron star equation state, which will give you the maximum mass for one single neutron star, right? So depending on the relationship between these two, we will have different central merger products. For instance, if we have two very heavy neutron star merge, and it will immediately collapse into a black hole. But if we have a less mass neutron star merge, in that case, maybe we have a temporal so-called hypermassive neutron star stage. It will survive 10 to 100 milliseconds, and then it will collapse into a black hole. Okay, so if we have two very light neutron stars merge, it may be merged into after the merge, it leaves behind a neutron star instead of a black hole, right? Of course, the neutron star may be initially it is supported by the rigid rotation, and after the neutron star spin down, it may collapse into a black hole, or it will stay to be a stable neutron star. So in principle, we have this full kind of merger product, okay? And also, beside the central product, we also have some ejected material surrounded this central product, right? Because during the merger, we have this tidal forces, and some materials could be ejected due to the centrifugal force, and it will form like a nearly isotropic envelope surrounding, okay? And the velocity of this ejecta could be 0.1 to 0.3 times of speed of light, and the masses of this ejecta could be 10 to the 4 to 10 to the 10 to minus 4 to 10 to minus 2 solar mass. And the total, so you can calculate the total kinetic energy of this is 10 to 47 to 10 to 49 ergs. Okay, so this is what we got from the numerical simulations. Okay, so we think that, okay, actually before the detection of 170817, before that detection, we already have built some kind of theoretical framework to tell you what kind of EM signal we expect. Okay, so people always say that, okay, so the signal depends on what's the central product. If the central product is a black hole, or it's a hypermassive black neutron star and collapse to a black hole in a very short time scale, so they have that could be a similar scenario, and we call it a black hole scenario. So in this scenario, we expect to have a short gamma ray burst first, because you have this black hole and you have some material falling into the black hole to form this accretion disk, and it will give you a relativistic jet, and this jet will power a gamma ray burst. And when this jet interact with the ambient medium, and it will give you a long-lasting afterglow. Okay, so okay, so in case that I don't know, in case that someone not familiar with gamma ray burst. So gamma ray burst is discovered in 1980s, 1960s, and right now we have studied this kind of phenomenon for more than 50 years. And it is initially we detect like very short gamma ray signals, so that's why call it gamma ray burst. But in all these years, we launched a lot of dedicated satellites to study this, and right now we know that it is not just a gamma ray signal, it also followed by very long time scale and multi wavelength signals. We call it afterglow. Okay, and it is isotropic distributed in the sky, and it is cosmic origin, because we detect the redshift, and also it related to some relativistic jets, relativistic motion. So that's a very basic stuff about gamma ray burst. And why we have this gamma rays, because we have this jet, and the jet have some discontinuous shells, and the internal collision of these shells, or you can call it the initial dissipation. The internal dissipation could give you this gamma rays, and when this whole blast wave interact with the medium, and it will create some external shock, and this shock will have synchrotron radiation to give you the X-ray, optical, all the way to radio photons. Okay, so that's the very basic theoretical framework for gamma ray burst. And we all know that the gamma ray burst is divided into two groups. One is when the gamma ray duration is shorter than 2 seconds, we call it short gamma ray burst. And when it's larger than 2 seconds, we call it a long gamma ray burst. And we guess, I mean, before, maybe even back to 1980s, we start to guess that the short gamma ray burst is from the binary neutron star mergers of neutron star and black hole mergers. But that's just a guess. But the detection of 170817 proves that indeed we have this short gamma burst from binary neutron mergers, right? But we need to remember that before that detection, we always say that because the short gamma burst is related to some relativistic jet, so it should have some collimation effect, which means we could only observe these guys when our line of sight is within the jet. Otherwise, we cannot detect that. So before the detection of 170817, before that detection, we never expect to see this kind of association because the chance of this is very small. But we have some surprise. I'll talk this later. Okay, and then so this is the gamma ray burst part. And also remember we have this ejector material, and this is nearly isotropic distributed. And this one is from the neutron star. So it is neutron rich. It have lots of neutrons. And in that case, these neutrons will give you some R-process nuclear reactions. And this will release lots of energy. It's just like the supernova scenario. And this will give you some optical transient, optical flare, and the peak time scale is around days and weeks. So this is initially proposed by Lee and Pazinski back to 1998. And in this letter, they okay, so they are motivated by their college, who is asking that what might be the observable consequence of binary neutron star mergers. And then they think about this, because they already know there will be R process happen and it will be energy release. So they just use those theory from supernova theory, and then they try to calculate what kind of signal. And I just want to say that back to that time, so all these very important parameters, they just put it by hand. Okay, so this F is how much fraction of those material could be converted into the heat. Okay, and this M is the ejector mass, and this is the ejector velocity, and this is the opacity, okay? And so with this parameters input, they predict that the signal could be even brighter than the supernova, because the supernova normally is 10 to 43, right? So they predict the signal could be 10 to 44. So, but the peak time is around 1 day. That's a very interesting prediction. After they make that prediction, some numerical simulations have calculate what's the ejector velocity and the ejector mass. And so it turns out what they put by hand, the parameter, at least for these two, is correct, right? So because when they use 10 to minus 2 and they use 0.3. So at least for these two is correct. But in 2010, the Metzger, Brian Metzger, so she is a very serious guy. She said that, okay, so maybe this F parameter is too large. They use 10 to minus 3, maybe it's too large. So he is the very first one to make a very careful calculation for those R process to try to see what's the F parameter. And after their numerical calculation simulations, they find that F is not 10 to minus 3. It should be 10 to minus 6. So in this case, this because this L is proportional to F. Okay, so you have 3 orders of magnitude lower. So in this paper, they predict that this signal should be, the luminosity should be 10 to 41, and it's just 1,000 times of the nova luminosity. That's why in this paper they call it kilonova, and that's where we start to call this kind of stuff kilonova. But I want to stress that in this paper, they just focus on this F parameter. And for the opacity, they still use 0.2, so which is commonly used in the supernova calculations. And later on in 2013, Dr. Kaysen, they start to thinking that, okay, so because this is different from the supernova, because in supernova you have S process kind of reactions, but right now you have R process. For R process reaction, you could end up with a lot of heavy element, and this heavy element could outweigh to even some less net elements, and those less net elements, they have very complicated the electron shells, and so in that case, the opacity could be much larger than 0.2. After calculation, they think that the opacity could be even 10. So it's almost 2 orders of magnitude higher. So in this case, the whole signal should be revised. So the first revise is the peak should not be in 1 day. The peak should be in weeks to 10 days. And also because this lessonness tends to absorb the longer wavelengths. To absorb some the blue wavelengths. So in that case, you will expect the signal tend to be red. Okay, so it should be red and peak in late time. So that's what they trying to argue. And okay, so but Dr. Metzger, they say that, okay, so what you said may be correct. So when we have some ejecta material have very high neutron fractions, it could generate less net. If less net elements is generated, we should use the opacity like 10. But because we have different kinds of, different contributions of this ejecta material. For instance, for the tidal material, it's directly from the neutron star, it should be neutron rich. It could have this less net. But in the polar direction, in that direction, the material may be ejected because the collision of these 2 neutron stars, and it is generated by the shock. Or maybe the material is from the disk. I mean, after merger, you have the black hole and you have the accretion disk. The disk could have some wind, and this wind give you this material. In that case, those materials don't have that high neutron fraction, and they don't have the ability to generate the lens nets. And in that case, it's still some 1 day peak, and it tends to be blue. So in this paper, they predict that maybe the kilonova signal should be red and blue. So we have 2 components. So to me, this is a very beautiful paperwork, and they predict this red and blue kilonova scenario. Okay, so this is a very brief introduction to the history of this kilonova. Okay, so different people call it different names. Maybe like Professor Li Xin Li in Peking University, they like to call it Lee-Pajinsky nova, and Dr. Metzger want to call it kilonova, and some people may call it micronova. But anyway, so it's just like it just corresponds to optical flare and peaks in days or weeks, and the luminosity is thousands of times of nova luminosity. Okay, and also don't forget that this material, they just not release heat. This material have a relatively high kinetic energy, and it will collect with those ISM medium, and this will generate generate some external shock. It's like just what I said for the gamma ray burst afterglow model, but this is not relativistic, so the shock is weak, but still it could generate some synchrotron radiation to give you a radio signal. But this signal should be weak, well, very, very weak, and it lasts for years or even tens of years or even hundreds of years. It lasts for a long time, but it's very weak, very difficult to be detected. Okay, so for black hole scenario, we have these three kind of signals. And well, like I said, so if you have this two light neutron star merger, it may generate a neutron star, and this neutron star may exist for hundreds of seconds or even exist for forever. Okay, so if you have this neutron star, everything will change, because this neutron star should have a very fast rotation because it is generated by the merger, right? So it should be rotate with the breakup limit. And also there should be, because it will have some differential rotation stage, and we could make a large magnetic field. So we expect to have a millisecond rotation and highly magnetized neutron star. And so if this is the case, this neutron star itself have a large rotational energy, and this rotational energy could be released by the dipole radiation, right? And this Poynting flux will carry lots of energy, and this energy would be released in some channels in the EM form in different channels to make us to see very rich and interesting signals. And so if the central product is a neutron star instead of black hole, we will expect to see a short gamma ray burst. And after the gamma ray emission, we expect to see the emission from this neutron star, right? Because this dipole radiation could generate a Poynting flux, and dissipation of this Poynting flux could expect to give us X-ray emission, like X-ray plateau emission. So we expect to have some short gamma ray burst and with late X-ray plateau emission. So do we observe this? Yes, we observe this in our short gamma ray burst samples. Okay, so the SWIFT 10-year detection detect around 100 short gamma ray bursts, and among these 100 short gamma ray bursts, about more than 20% have this kind of so-called internal plateau. What is internal plateau? So it's X-ray plateau emission, and after the plateau, you have a very steep decay. So it's very difficult to explain this steep decay within the black hole scenario, because it's just very difficult to explain this, because you have a black hole there. If you have some fallback, it should be follow some certain slope. It should not be this steep. But if it is a supermassive neutron star, it could explain well, because at this point, the neutron star will collapse into a black hole. When it collapses, nothing will release anymore. In that case, you will expect a very steep decay. So we do see this kind of emission from the short gamma ray burst signal. So which means this prediction should be correct. Okay, and also in some direction, maybe some open direction, this internal plateau could be this X-ray plateau emission could be observed without short gamma ray burst, because we already say that the short gamma ray burst should have some collimation effect. In other directions, we cannot see that, but this dipole radiation from the neutron star should be nearly isotropic. So we may see some often X-ray plateaus. Do we see this? Yes, we also see this. So this is a Nature paper published in, I guess is in 2020s. And in that paper, they searched the X-ray signals from the Chandra observations, the archive data, and they found this often X-ray plateau emission. Okay, so we do have this often X-ray plateau emission, but this should be have a small chance because, like I said, you have a nearly isotropic surrounding material, and only some open zone. In most of these directions, this Poynting flux could hit on the material. And if this Poynting flux hit on the material, it will have two effects. One effect is it will hitting this material. Okay, so without this Poynting flux, the material could be heated by the R process, right? But right now you have this additional energy injection, and this energy injection could be much larger than the R process. In that case, this so-called kilonova could become much brighter. Okay, so maybe we don't call it kilonova because it's no longer kilo. So maybe we suggest to call it merger nova because it's from merger. Okay, and also this energy could not just heating this material, it could also accelerate this material to make this ejected material to mildly relativistic or even relativistic. And in that case, the interaction between this material and the ASM could be a strong shocked scenario. And in that case, it could give you not just a radio signal, it could give you even optical or X-ray signal. Okay, so do we see this kind of stuff? Yes, we in the short gamma ray burst data, we do see some very bright optical signals like what we predict, like the merger nova. We do see these signals, and also we do see those we do see this broadband non-thermal signals from this kind of shot. Okay, so I don't have time to go too much details. I list the reference here. So if and I will send the PowerPoint to Sarah later. So if you guys have interest, you can read all those reference. Okay. Okay, so the picture is like this. What's the signal? What's the EM signal? It depends on the central product. If you have a black hole in the center, you have this three: the gamma ray burst, the kilonova, and this radio signal. If you have this neutron star, the kilonova will become brighter, and we also expect to see some X-ray plateau follow this short gamma ray burst. So that's the bottom line. Okay, so let's recall our memory about this detection of 170817. So in this one, we do observe the short gamma ray burst and the optical trends and X-ray and the radio. It seems everything is perfect, is following the whole theory, but actually I want to say it's not that perfect. So we still have some surprise. For instance, like I said, we before this detection, we don't expect to see short gamma ray burst because this collimation effect. But why? For the very first detection, we see this short gamma ray burst. So people start to say that maybe this short-gamma burst is not normal one like we say, like we see in before, because let's see its isotropic energy or its luminosity is 2 to 3 orders of magnitude lower than the normal ones. And also, so in this case, people try to use the structure jet model. Okay, so the model is like this. So you have a jet in the center, and when the jet punches, the jet need to punch a hole in the surrounding material, right? In order to get out. So when it punching the hole, it will dissipate energy into the material surrounding the jet, and it will bring all this material out. And this material should have a relatively lower energy and lower speed, and it will form like a wing structure around the jet. Okay, so what we see for this one is not the jet part. What we see is the wing part. So that explains both why we see this for very first detection, because if you have this a wing structure, it will largely increase the detection probability for you. And also because the wing structure, the energy is lower, so that's why we see a relatively less energetic short-gamma burst. Okay, so that's one surprise, and now we're trying to use this model to explain this surprise, the structure jet model. Okay, and also for this optical transient like the kilonova. So the kilonova is what we expect. We see first we see a blue component, and then we see a red component. It seems perfectly like what predicted by Dr. Metzger, but let's focus on this peak luminosity. Let me recall that why we call it kilonova, because it should be 10 to 41, because the ejected material have some sort of mass limit. It should be less than 10 to minus 2 solar mass. And if you have this mass limit, you cannot access the 10 to 41 ergs per second. But now we have this 10 to 42. So if you want to use that model to feed the data, what you got is the total mass budget should be larger than 10 to minus 2. So why is that? Because before this detection, all those numerical simulations never gave us this high ejected material. So it is so-called the ejector mass issue. So because if you believe all those numerical simulations, and you need to have very large mass ratio between the two neutron stars to give you this amount of ejected mass. And people trying to argue that, okay, so maybe the majority of the mass is not from the tidal tail, is from the disk wind. So if we, in that case, because the disk wind is not quite related to the mass ratio, in that case, it could solve this ejector mass issue. So if you guys have an interest, you can read this living review by Dr. Metzger. It have a very detailed explanation for this. And also some people think that maybe this is the hint that the merger product of 17017 is not a black hole, it's a neutron star. Like we predict, the neutron star will enhance this the kilonova, so it becomes brighter. So some people trying to argue that, but my idea is that, yeah, so you cannot rule out the merger product is neutron star, but the neutron star should be in a very weird situation. It should have a very fast spinning, but it should have a very weak magnetic field. It is no longer a millisecond magnetar because the magnetic field cannot be large. Otherwise, it cannot violate all those radio and the optical observations. Okay, so that leaves us another open questions. What's the merger product of this event? Okay, so I think I use up my time. I just want to leave this page here. I mean, I list many references. So right now we already entered this new era of GW and EM joint detections, and people already use this joint detection to do lots of stuff like measure the Hubble constant, and also test some gravity theory to constrain the neutron star equilibrium state, study the arranging of heavy elements, and study the properties of short gamma ray burst. So all in all, the binary neutron star merger is a very good candidate for us to make a multi-messenger observe, and use that we could do lots of things. Okay, thank you.